This is a quick video on C13 NMR multiplicity, and basically what that comes down to is how many lines are in a given peak. So a peak is a signal, a grouping of lines, and so on. And in proton NMR, things end up looking quite complicated, but C13 NMR is really straightforward. C13 NMR peaks are singlets. That's the end of the video. Short video. I'm being told that that's not quite true. I don't buy that. Contemplate ethanol, for example. 2 carbons, that's all that's going to show up in the C13 spectrum. One of them's near an oxygen, so let's say right around 60 or thereabouts. And one of them's kind of a boring methyl, so, you know, maybe 10 to 20, so 15. That's what you'd expect. 2 lines, and that's it. They're going to be singlets. What else is there to think about?
See, this is what I'm talking about. We got 2 lines. The one near the oxygen and the methyl. Singlets. Zoom out? Why should I zoom out? Oh, what's that?
I'm being told by my fake producer that I really should pay attention to the fact that I already told you that 77.16 for CDCl3 is always going to show up as 3 lines. That's pretty compelling. All joking aside, C13 NMR's peaks usually are singlets, but that's not because they have to be. That's because we choose to collect spectra that way for pretty good reasons. But why would peaks not be single lines is a fairly complicated answer that's actually better to illustrate in C13 spectra, where the understanding of it is relatively straightforward, and then we can go and deal with it in proton spectra. So the key thing to keep in mind is the reason why a line shows up in multiple places has to do with energy levels. So imagine you have a carbon and a hydrogen, and we're going to ignore what else is on this system. So we're just thinking about this system right here. The reason why we are able to see a C13 in the actual spectrum is because this isotope of carbon specifically has a spin to it. There is a spin 1/2 or spin minus 1/2 possibility. And the reason for that is more or less because the nucleus contains an odd number of protons and neutrons. So C12 doesn't show up in the NMR at all. C13 does show up in the NMR. And more or less what happens is that there's some energy level for, say, the nucleus, but as soon as you put this in a super strong magnet, what that does is create 2 energy levels. And more or less, the carbon nuclei are going to split just about exactly 50-50, but not quite. There's going to be a slight preference for being more in this population and less in this one. The energy difference here is tiny, but there's going to be more nuclei essentially in this bottom population because it's lower energy than in the top. And so the way you actually collect the spectrum is you hit it with a pulse, so you provide a whole bunch of energy into the system, and molecules that are in this energy level pop up, and then you wait for them to decay back down, and when they do, that's when you're listening. You're listening to the response, and some energy is given off, and so you sense through the radio waves that this exchange has taken place. So normally what happens, and we get a line for this, we get a line for this gap. That's what gives rise to a line in a C13 spectrum. And so if we're collecting our C13 spectrum, it would show up, say, right there, arbitrarily. You would get 1 energy for this gap right here. But notice what I've ignored so far is the influence of the hydrogen. And we know, of course, that hydrogen atoms provide their own spectra. And that is because hydrogen atoms likewise have spin 1/2, plus 1/2, minus 1/2. So the energy gap in the carbon nuclei is what gives rise to the line that you see in the C13 spectrum. But now let's call that energy right here, and we say that this carbon atom by itself has a certain energy that it experiences within the magnet. What will happen then is the influence of the spin 1/2 proton, which again is NMR active, is going to split that energy level into slightly lower and slightly higher. And the reason why is best understood as you have this giant magnet, and it's got this energy for the magnet that's, let's say, providing a magnetic field in, say, that direction. And then your hydrogen atoms can either be aligned with that, slightly increasing the energy that the carbon experiences, or they can be anti, which would slightly decrease the energy that the carbon nucleus experiences. And so in other words, your single carbon atom, in the absence of a proton, which would show up at this line, then becomes split into 2 lines. So again, you have 1 energy level for the carbon by itself, and then you have an energy level where the hydrogen is pointing in the opposite direction of the magnetic field, and an energy level where the hydrogen's aligned with the magnetic field. And so this carbon goes from being 1 line to being 2. It goes from looking like a single line in the C13 spectrum spectrum to instead looking like two lines in the C13 spectrum split slightly apart versus where that original line was. If here's where that carbon was going to be, now you have two energy levels, one slightly above and one slightly below. So if this is where the carbon resonance was going to be observed in the spectrum, now you have two such lines. So your singlet becomes a doublet from the influence of a single hydrogen. Okay, so what if we now have a carbon, a C13, that has two hydrogens bound to it? And again, I'm not specifying what else is out there. How does that change the picture? Well, so once again, I ask you to imagine that you have a giant magnetic field sitting right there, which is the superconducting magnet that we're using. And then we have these spin-a-half situations, so the hydrogens can either be aligned with each other or not. And that actually leads to four cases. There's going to be the case where both hydrogens are straight up. There's going to be the case where both hydrogens are pointing straight down, they're spin down. And then you have two cases, one where the left one is up and the right one is down, and then one where you've got the opposite. So there actually ends up being four energy levels created. But as far as the carbon is going to experience, well, what it's going to experience is one where the two hydrogens cancel each other out, and another where the two hydrogens cancel each other out, as well as the case where both hydrogens are increasing the magnetic field, and one where both hydrogens are decreasing the magnetic field. And so in fact, your carbon then ends up splitting into three different lines, and if you were to resolve what it would look like in the actual spectrum, well, you're going to get three different lines, one in the middle, twice as tall as the two on the side. Why? Because of this splitting, because the spins of the hydrogens involved are either going to be both in the same direction, adding to the magnetic field of the magnet, both opposing the magnetic field, or more likely, where they oppose each other. And so you have 25%, 50%, 25% chance of each scenario, give or take, and that gives rise to this picture. Okay, so now let's be specific about why deuterium behaves the way it does. And that's because C13 NMR spectra are singlets given the way we choose to run them, but even in the scenario where we are suppressing all of the carbon-hydrogen coupling, the sort of different peak shape from the hydrogens involved, then deuteriums are different than hydrogen. A deuterium is a hydrogen atom that has an extra neutron in it. And what that means is the spin for the hydrogens is usually spin a half for a proton, but the spin for a deuterium is spin 1. And the reason why that matters is because there are actually three spin states possible if you have spin 1. That is a spin 1, spin 0, spin minus 1. Whereas when you have spin a half, like the carbon, then the scenario is plus a half and minus a half. So the carbon atom is plus a half, minus a half, but the deuterium is spin 1, spin 0, spin minus 1. So in practice, of course, the key thing to keep in mind is that your carbon atom is now going to be split into three energy levels. One where it's not affecting the magnetic field at all, one where you're adding to the magnetic field, and one where you're subtracting to it. And so that will give rise to three lines. So if you had a way of suppressing the carbon deuterium signal, then you would have a single line at 77.16. And that's because in the absence of the deuterium, if you're just looking at the carbon itself, it would want to show up to 77.16. But the presence of this 1, 0, minus 1 energy levels, what happens is that single line gets split into three equal lines. And the reason why it doesn't look like a 1, 2, 1 scenario like in the... It's because here you actually had four energy levels, two of which overlapped. And here you just simply have three energy levels, and you have an equal probability of achieving each one. So that's what's going on there. So in other words, I wasn't lying when I said at the outset that the ethanol is likely to give rise to two lines in a standard carbon spectrum, one that's say 60-ish and one that's say 10 to 20-ish, maybe 15. And if you were to expand out, if we had TMS in the sample, it would show up at 0, and you would have CDCl3, the three-line pattern from the deuterium, showing up. And this is what happens when we run the carbon in a decoupled manner. Basically, it's hard to see the other peak shapes. It's easy to see single lines. And the standard abundance, natural abundance of C13 is 0.01. It's 1%. About 1% of all carbon atoms are C13. And so our signal is going to be really bad anyway. Anything that makes our C13s harder to see is bad. And so let's just suppress all of the hydrogen signal, which is relatively easily done. And what that will do is allow us to see more carbon atoms easier and better signal to noise and stuff. So that's why we choose to run it that way. But what would it look like if instead we were paying attention to the hydrogens involved? What if we ran this coupled decoupled. Well, you're still going to see the exact same thing for the deuterium. Again, the deuterium's not a standard hydrogen, so it's not going to behave any differently. And let's ignore the TMS. So the TMS would still be down here at 0, but let's ignore what that would look like. Okay, so what's going to change now is that your ethanol lines are suddenly going to be split by the nearby hydrogens. These two hydrogens together are going to make sort of a triplet shape. And so for the carbon that was closer to 60, that's now going to resolve to look like a triplet by the experience of having the nearby H's, the H's that are bound to that single carbon. Meanwhile, 3 of them together are going to add to form what we would term a quartet. And so this is what you're going to see for the C13 spectrum for ethanol. Of course, it looks that way because you have 3 hydrogen atoms, and therefore the scenarios end up being 8 in total. One energy level where all 3 hydrogen atoms are aligned down, one energy level where all 3 are aligned up. But there are 3 different ways to have 2 up and 1 down, and there are 3 different ways to have 2 down and 1 up. And so the total is 8 different line segments, and the way it ends up looking is 1, 3, 3, 1, or the way it'll show up in the spectrum is 1, 3 times taller, 3 times taller, 1. Now, of course, things are never quite that simple. As it turns out, the further away hydrogens are going to start playing a role, and that will complicate this image somewhat, but this is the idea.
There are a couple of finer points to make. I've already splashed this image up on screen. If I put the top of the CDCl3 line up here relatively high on the screen, you will observe just how small the triplet and the quartet are. Whereas, by contrast, with the CDCl3 at roughly the same relative level, you'll notice the singlets show up much better. And so you get much better signal to noise. These are much more visible than triplet and quartet. Another thing I'd like to point out is, of course, the middle of the triplet is precisely where the one line is, and the middle of the quartet is precisely where the other line is. And that's an important feature to keep in mind. But then the last point I was making with regards to how complicated the spectra actually looks, if you zoom in tight on these nominal triplets, what you see is that actually each one of these lines is a quartet, which is kind of annoying and complicated. And likewise, if you zoom in on the quartet and you zoom in really tight, you can see that there's some kind of weird feature going on here as well. Though at first glance, you would call this a triplet and a quartet, and you would be right. If you zoom in tighter, you can see that the further away hydrogens are playing some role. We'll discuss this more in a future video.
Finally, there's one great question that some of you may be thinking of already, and that is, if both of these atoms are spin a half, couldn't they cause each other to split? Couldn't you get coupling between the 2 carbon atoms right there? And the answer is yes, absolutely. That is something that can happen, and that would definitely complicate our spectra. And here, the fact that C13 is naturally not very abundant works very much in our favor. If the chance of any one carbon being C13 instead of C12 is 1%, then the odds of having 2 NMR active C13 carbons next to each other is more like 1 in 10,000. That's really not happening at a big enough level for us to be able to see it. So what you're seeing is the 1% of carbon atoms in a given spot are a 99% chance of having nothing coupling to them nearby, and a 1 in 10,000 chance of seeing the coupling of the nearby carbon atom. So generally speaking, we don't worry about carbons coupling to other carbons because the odds of that happening are so low, and generally speaking, we choose to suppress the multiplicity that would result from having the hydrogen information contained within our C13 spectrum. So we run our NMRs in such a way that C13 peaks are singlets for the ones that have H's attached, and if you see something that's not a singlet in the C13 spectrum, it's probably because you're looking at a deuterium. You're looking at the solvent. So the 3-line pattern is CDCl3, and if you see that sort of regularly spaced pattern showing up in your C13 spectrum, check to make sure what solvent you're using. If it's a 3-line pattern, all the equal height, you're looking at CDCl3. If it's more complicated than that, you may be using this in DMSO D6 or the equivalent.